Hello, my name is Eric Chan, and I'm the CEO of CavPoint. CavPoint is a startup working on software tools for automated vehicle development. Today I'll be talking to you about some of the work that we have done recently on accelerating the virtual validation of automated vehicles using data-driven optimization. There are many challenges for the mass deployment of automated vehicles in complex environments. But the main challenge is to do with the safety assurance, which has to assure that the whole system will behave correctly under all situations. This will need an extensive testing, verification, and validation process. For a typical safety-critical system, the cost of this is usually around half of your engineering budget. But for automated vehicles, it's likely to be higher than this because we have a very complex safety-critical system operating in a very complex and varying environment. It's generally accepted that the testing will take place in a number of different forms. There'll be physical testing of vehicles on the open road. There'll be software in the loop testing, hardware in the loop, but there will also be an extensive use of simulation all the way through the development program. It's also generally accepted that this will be scenario-based as opposed to mileage-based. So when you have scenario-based testing, you have a whole set of base scenarios that your system has to operate under, and then you have to develop your system and test your system based on these scenarios. Now, each base scenario will actually generate an enormous number of scenario variants when you look at all of the things that can vary within that scenario. And this will lead to a combinatorial explosion of cases that you have to test. So how do you find out which of these combinations actually cause problems for your system? So let's take an example of a scenario and see what type of variations could occur on that scenario. So first of all, we have the road geometry or the road topology that can change, and this will typically change over a time scale of months or maybe days. And then we have traffic speed and density, weather, and lighting. And this can typically change over a time scale of hours or minutes. And then we have what might be the most unpredictable change, which is other driver behavior. Other drivers can act in a very aggressive way, or they can operate in a very polite way. And this can typically change over the course of minutes or even seconds. And then the sixth one is unpredictably moving objects. We can have animals on the road, and it's very hard to know what they will do. So if we take, for example, these 6 variations and we look at 12 variants for each of these 6, we already end up with almost 3 million different combinations. So the way that we would explore this in simulation is shown in this next slide. So we have a database where we have a number of base scenarios and a number of scenario variations that we will apply on each of those base scenarios. And then we will take one of these base scenarios and its associated variations and create a number of concrete scenarios. And these are scenarios that have actual values for all of the variations. We can then run this within a simulation environment. And this simulation environment will be connected to the automated vehicles perception and control software. So what we are doing within CavPoint is we are focusing on these 2 blue boxes on this slide. The first is after each simulation has run, we will calculate a number of KPIs or key performance indicators. And this will give us a measure of how the AV vehicle has operated under these particular conditions. We then use these KPIs to create new tests. And basically, the aim of what we're doing is we're trying to look for problematic events that are starting to happen, and we are trying to drive the system towards finding these problematic events, to triggering these problematic events so that we can then study them and resolve them. So we are focusing on these two blue boxes. And in order to do this, we have to have a simulation environment, and we're using CarMaker. And we have to use some perception and control software. And we are using the ACC software that's built in within CarMaker. What we also need is we need to have a base scenario and scenario variations that we're using to develop our techniques and to use as a case study for us to work on those. So the driving scenario that we have selected is one that uses ACC, Adaptive Cruise Control. And we're basically doing a cutout scenario, and it's based on Euro NCAP's 2018 automated driving tests. So what happens during this driving scenario is that here in yellow, we have our ego vehicle, our automated vehicle, and it is basically driving on the highway using Adaptive Cruise Control, ACC, and following the orange vehicle. So this is a stable situation. And then what happens is that the orange vehicle changes lane and moves out of our lane, revealing to our ego vehicle this black vehicle. And the black vehicle is also moving. It's not stationary, but it's moving at a slower speed. And so what this means is that our ego vehicle here has to slow down, decelerate, or brake to adapt to this new situation. And the orange vehicle that has changed lane just continues on in the other lane. So now that we have the scenario, the base scenario, we have to identify the scenario variations and the KPIs. So if you first look at the scenario variations, we are using 3 different types of scenario variation parameters. We're looking at how the ego vehicle behaves, our yellow car, our AV yellow car. We're looking at how the other vehicles behave. There are 2 other vehicles. And we're also varying the ACC control parameters. And we have ended up with a total of 7 types of scenario variations. So each of the tests we're running, we will be changing 7 different aspects of that scenario. And that effectively means that we have a 7-dimensional problem space. So each test is located within a 7-dimensional space. So we've also identified a number of KPIs, key performance indicators. So we have chosen for this test to use safety-related KPIs. But in the future, we may also use other types of KPIs which are not safety-related. Now, these could be objective KPIs or subjective KPIs. Examples of these, for example, are the effect of our actions on the other vehicles in the environment or on the traffic flow in general. Another example could be the passenger comfort for occupants of our AV vehicle. For example, is it jerky? Is it uncomfortable? Is it hesitant? So let's look at some of the results of running this scenario. As I mentioned before, we're carrying out an active search for the problematic variants of our base scenario. And let's have a look at some of the results of doing this. We have defined a particular condition that we define as problematic. And this condition is naturally present in about 0.06% of our 7-dimensional test space. This is quite a rare occurrence, and this represents our needle in the haystack that we are now searching for. In this example, After about 20 iterations of our optimization algorithm, we increase the detection rate of this condition from 0.06% to around 70%. And this represents an increase in detection rate of about 1,000 times. After this iteration, the rate of detection stays around the same. It moves up and down a bit. So if we look at the later iterations, and we now have quite a lot of data for the problematic scenarios. And let's have a slightly more detailed look at this data. So here we have a plot where we have basically plotted the results of the tests over the later iterations of our optimization. Now, all of these test points, of course, are in 7-dimensional space. So what we have done is that we have used some algorithms to convert from 7-dimensional space to a 2-dimensional space. And that is the plot that you can see on this slide. What we have also done is that we have used clustering algorithms to identify the clusters for these points, because it can be seen that a lot of these points seem to cluster together. And the reason they're clustering together is that many of these test points, they actually represent different tests, but they actually all represent common conditions or common issues. So it makes sense to cluster them together. And the reason it makes sense to cluster them together is that in the past, I have used various software to find faults, and it will sometimes report hundreds of faults. But when you actually look into them, many of the faults that are reported are actually due to one cause. What we're doing is we're reducing all of the errors that we're finding into a smaller number of clusters. So on this plot, we have over 350 test points that meet our condition that we're looking for. But instead of reporting 350 errors to the end user of our software, who will be an AV development engineer, instead of reporting 350 test cases, we cluster them together and report back the clusters. And in this case, we're reducing over 350 test points to 7 clusters. And that's a 50 times reduction in the reported issues to the AV development engineer. And what that means is that it's easier for them to understand what the issue is, to resolve it, and to carry out tests afterwards to test that it has been resolved. So let's look in a bit more detail at some of these clusters. So these clusters of test points, of course, all exist in the 7-dimensional space. But when you actually look at each cluster, the things that vary for that cluster, the characteristics of that cluster, are that not all of the 7 dimensions are varying. And typically it's only a few of the dimensions, and each dimension is a scenario variation. Usually it's only a few of these that matter for that cluster. So what we have done here is we have taken 2 of our clusters, identified which are the most important variations or dimensions for that individual cluster, and then plotted it on a 3D plot, which is a lot easier to visualize. So here, for example, this is the plot from the previous slide. And if we take this cluster, which is cluster number 0, and we identify its 3 main dimensions and plot it on here on the left, you can see that it's quite a small cluster. If we take this other cluster, which is number 2, and we plot it along its 3 most important dimensions, we see that it's a more elongated cluster. The axes that we have on these plots at the moment are normalized axes, so they go from 0 to 1. But what we would eventually do on here is that we would put in the engineering units for this dimension. And that would make it easy, for example, to see that a particular cluster occurs between speeds of, let's say, 45 to 50 kilometers per hour, for example. And this allows the AV development engineer to have a good picture, an image of what is causing that cluster, of erroneous or problematic test points. To conclude, we are a startup developing software tools to reduce the costs of AV development. We're currently at a relatively early stage and still developing our proof of concept and our core technology. But this has shown some promising initial results. We have managed to show a 1,000 times increase in the faults found using our optimization algorithms and our KPIs. And once we've found all these faults, we have grouped them together into common root causes. And by doing this, we have produced a 50 times reduction in the number of reported issues. And this means that the end user, the AV development engineer, will find it a lot more easy to understand and process that information. We have been carrying out this work using two different base driving scenarios. One of them has been an urban driving scenario, where we have our AV coming out of a T-junction. But the vast majority of our work has been done with the driving scenario that we have shown in this presentation, which is the ACC driving scenario. Our next step is to carry out a pilot project with a customer. This will allow us to further develop our technology using different driving scenarios and different and more complex AV software, which will be the customer's AV software. And this will also allow us to take into consideration the requirements and the constraints that the customer will have. Finally, we would like to acknowledge the help and support of IPG Automotive with their car maker simulation software. And we'd also like to acknowledge the help of the UK Department for Transport, as we have received a T-TRIG grant that has helped with this project. Please do not hesitate to contact us if you would like to find out any more about what we've been doing. Thank you.